So with de Broglie having done his work and Heisenberg having done his work, that ushered in the opportunity for Schrodinger to basically do some giant math that allows us to predict with pretty great accuracy where an electron is within reason, according to Schrodinger, and using the fact that it behaves both as a wave and a particle, according to de Broglie. So basically, the short form for Schrodinger's equation is h wave function equals e wave function. And again, you're not going to do any math with this at all until you take something like physical chemistry in college, but you should be aware of Schrodinger's equation, and more specifically, you should be aware of what it tells you, and the most important thing that it tells you is the actual probable location in space of an electron with a very specific energy. So to go through that a little bit, here's the math, or I'm sorry, here's the data that allowed Schrodinger to figure this out. So what he said was that they basically paused the world and collected position data for a hydrogen electron hundreds of thousands of times. And when they did that, they created a plot. And the plot looked something like this. So that hydrogen electron had all those little dots. And as you see, going from the center out to the edge, the radius, the dots get less and less dense. So the probability of where an electron is actually located is where the denser part of that plot is. So basically, Schrodinger was able to come up with the idea that the first energy level is where the first electron's located in, and because of the data, it shows up acting or behaving like a sphere, which is this. So in the energy level, the first sublevel is the S-shaped sublevel, which is spherical in nature, and he also determined that the S can only hold 2 electrons total. Now, so this is the sublevel of an actual energy level. Now, another sublevel that he was able to kind of take a look at was based on the fact that there are multiple S sublevels. So the first S sublevel in energy level number 1, which would probably relate to atoms like hydrogen and atoms like helium, had a very, very specific size, but the density of the electrons was still the same. That is, they were closer to the nuclei. Now, for the second energy level, which is this part right here, is basically any of the atoms that are located in the second energy level. So atoms like lithium and to neon. We're living in this sort of white space right here. And that was the second S sublevel. And again, that can only hold 2 electrons. And then the third one was this gap or this space from roughly here to here. So that's the third S sublevel. S. So in that case, so they're talking about atoms like sodium and magnesium. And actually, I misspoke about the other one. It shouldn't be neon. It should be lithium. It should be lithium and beryllium. Okay. So the other thing that I want you to sort of see is that each S sublevel stacks upon itself, and when it stacks upon itself, they become like layers. So the first S sublevel, and then the second S sublevel stacks on top of it, and the third S sublevel stacks on top of that. But each of them is in a different energy level. There are other possible orbitals or orientations, and those are your p orbitals. So on the board, I've written this a couple of times, that the p, x, py, pz, although I didn't do x, y, and z, but when I was drawing them, I would do arrows, like arrow up, arrow up, arrow up, and then arrow down, arrow down, arrow down. So each individual p orbital can hold 2 electrons, for a grand total of 6. And if an arrow equals an electron, that means that the p sublevel can hold 2 electrons each. So we now have an energy level, we have the sublevel, and then the sublevel has different shapes, so those are orbitals. So we have energy level, which has sublevels, which can have different shapes or different varieties. So then we have orbitals. And that's pretty much all the further we're going to get. But there are other orbitals that exist. So in the 3rd energy level and the 4th energy level and the 5th energy level, here's your transition metals. Okay, we have a different orbital that's called the d orbital. And so the d orbital has this shape like this. It's got 4 or 5 different, so it's got 5 different shapes, but we're only going to concern ourselves with the fact that the d orbital exists. So like if I were to draw it out on the board in an orbital diagram, I would have d, 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 and arrow up, arrow up, arrow up, arrow up, arrow up, arrow down, 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 down. So they can hold the d orbital, the d sublevel can hold 10 electrons. But each d orbital can hold 2 electrons. So the p sublevel can hold 6 electrons. Each p orbital can hold 2 electrons. The s sublevel can hold 2 electrons, and each s shape can hold 2 electrons. So here are the other different orientations of the d orbitals, and then them all stacked on top of each other. You're never going to have to be able to see this or be able to draw this. You just need to know that there are 5 of them, and each of the 5 can hold 2 electrons. And then there's the 7 f orbitals. So if I were to draw it out, 3, 4, 6, 7. Again, that would look something like this. Arrow up, arrow up, arrow up, arrow up, arrow up, arrow up, arrow up for 7, and down, 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 down for 14. So in your f orbital, or f sublevel, can hold 14 electrons, but each f orbital can hold 2 electrons. Okay, so those are your different orientations. Now, it appears okay. Oops. So there are some other things that we need to keep track of. Those things we need to keep track of are what the different things mean. And I referred to this a bunch of times, and I said I was going to get to it in a lecture, so here we go. There are different quantum numbers that describe different atomic orbitals. So for example, or what they actually mean. So n refers to the principal quantum number that describes the energy level. So that can be 1, 2, 3, 4, 5, 6, or 7. That's it. L refers to the angular momentum quantum number. The angular momentum number describes the shape of the orbital, whether it is an S shape, spherical, a P shape, bow tie, or barbell shape, D shape, or F shape. Each of those has a value of a 0, P, a 1, 2, or a 3. And then the ML is the magnetic quantum number, and it's an integer from -1 to +1, and it describes the orientation of the orbital, that is, in what 3-dimensional shape it's in. So when the magnetic quantum number is equal to, when the angular momentum number is equal to 0,